Section 3.1, Differentiation Rules. We have three objectives in this section. The first one is to use the rules to more easily determine derivative functions. We want to also determine higher order derivatives, and finally apply derivatives to problems involving tangent lines and business applications. So we begin with the basic differentiation rules. So far, we've been finding derivatives using the definition of the derivative, meaning the limit definition, and we've seen that it can be extremely tedious and sometimes even difficult to find the derivatives that way. In this section, we are going to learn several shortcuts that can help us find derivatives more quickly. So the first rules that we're going to come across are these four, and they are the basic rules of differentiation. And in these rules, f of x and g of x are functions, and n and c are just random real numbers. So the first rule we have says that if you are taking the derivative of a constant, the answer is going to be 0. So if I ask you for the derivative with respect to x of something like 5, you're going to say 0. The derivative with respect to x of pi, for example, because pi is 3.14 and so on and so forth, the answer is also going to be 0. So anytime you have a constant, the derivative of the constant is going to be 0. The second rule is the power rule, and this is known as the simple power rule. It basically tells you what to do if you have x to the power of n and you want to differentiate it. And according to the rule, all you got to do is bring the power down, then subtract the original power by 1. So for instance, if I have something like the derivative with respect to x of x to the power of 3, then according to this rule, all I have to do is bring the power to the front, so I get 3, and then subtract the original power by 1. So 3 minus 1 is going to be 2, and the answer is going to be 3x squared. Now be careful when applying this rule. If the x is on the denominator, it needs to be written on the numerator first before we can apply the rule. So if I have something like derivative with respect to x of 1 over x squared, for instance, I cannot apply the rule directly. I have to rewrite the problem with the x on the numerator, so it's going to have a negative power. And then I do the same thing that the rule tells me, which is bring the power down, and then subtract the original power by 1. So it used to be negative 2, and then when I subtract 1 from it, it becomes negative 3, because negative 2 and we're subtracting negative 1, so the total will be negative 3. Now, the next one, it tells me what to do if I have a constant times a letter, or a function in general. And it basically says just ignore the constant and just differentiate the x's. So for example, if I have something like the derivative with respect to x of 5x cubed, then according to this rule, I just ignore the 5 and I differentiate the x's. And we know that the derivative of x cubed is 3x squared, so we end up with 5 times 3x squared, which you can also rewrite as 15x squared. So this is known as the constant multiple rule. Basically, ignore constants if they're being multiplied, but if they're alone, then we use rule number 1 to just put 0. And finally, the last rule basically tells me what to do if I have an addition or a subtraction of variables. And according to this rule, we just separately find the derivatives of each individual component. So if I have something like the derivative with respect to x of x cubed plus the derivative of 1 over x squared, then all I have to do is find the derivatives individually. So derivative with respect to x of x cubed, and find the derivative of 1 over x squared with respect to x. And we already know the two answers are 3x squared minus 2x to the negative 3. So basically, I'm allowed to do this whenever I have a plus or minus in the middle. So if it was a negative instead, then the answer will be basically the same, except the minus here would have to be changed because of the product of the two things. So those are the basic rules, and now we're going to actually put them to good use by finding derivatives of functions. So imagine having to do the derivative of this expression, for instance, with the limit definition. It would take maybe 2 to 3 hours to finish, but with this rule, you'll see the answer comes out very, very quickly. So the first thing I'm going to do with these problems is write down the original problem. The y is 2x4 plus 9x cubed minus 6x squared plus x minus 5. And I'm looking for the derivative, meaning I'm looking for the dy over dx, also known as y apostrophe, y prime, or dy over dx. That's what represents the derivative. And so first things first, I have a bunch of pluses and minuses, and according to the fourth rule, we can just ignore those pluses and minuses and just take the derivative of each individual components. So I will find the derivative to x4, I'll find the derivative of 9x cubed, then 6x squared, then x, then 5, and I'll add or subtract the answers depending on where it used to be there. And so for the first term, the 2x4, according to rule number 3, there's a constant times a variable, so we ignore the constant, and we just find the derivative of x4. And according to rule number 2, the derivative of x4 is 4x cubed. So bring the power down, then subtract 1 from the original power. So remember, there used to be a product between the 2 and the x4, so there's still a product between the 2 and the solution that we just got. Next, there's a plus sign, and according to rule 4, we ignore the pluses or minuses, and we continue as we did before. So 9x cubed, we ignore the 9, we differentiate the x cubed, it becomes 3x squared. Next, we have a minus, and so again, we ignore the minus, we have 6x squared, we put the 6, and we differentiate the x squared. The derivative of x squared is going to be 2x to the power of 1, because we're subtracting 1 from the power, and by the way, when the power is 1, we don't have to write it down, we could just write 2x instead. Next, we see a plus sign, so we'll put the plus and find the derivative of x. So derivative of x, well, x has power 1, so we bring the power down, then we subtract the original power by 1, so 1 minus 1 is going to be 0. And by the way, x to the power of 0 can be rewritten later on. We're actually going to replace x to the power of 0 with just 1, because that's what it is. So anytime you have a base to the power of 0, you're going to write 1. So this will become a 1 later on. Finally, we have a negative, and so we ignore the minus sign, and we need to find the derivative of 5. And the derivative of 5 is actually just going to be 0, because it's a constant without a variable. And that's rule number 1. So we used a bunch of rules. All of the rules that we've learned so far, or that we mentioned so far at the start section, got applied in the same problem. So the derivative that I'm looking for, the dy over dx, or in other terms, the y prime, doesn't matter which one you pick, they're both the same. Then what's the derivative going to be? Well, 2 times 4 is going to be 8x cubed, and then we have 9 times 3, which is going to be 27 with the x squared. 6 times 2 is going to be 12 with the x, and then finally 1, and like we said, x to the power of 0 is really 1, and 1 times 1 is going to be just simply 1. And finally, there's a 0 at the end, which I don't need to write, and that's the end. So this is my final answer. So as a reminder, we are going to recall that if I have a base with x to the power of 0, that's going to be equal to 1. So we're going to do this process multiple times, so let's go ahead and practice. And I would recommend before we start each one of these parts that you pause the video and see if you can get the answer on your own first before you look at the solution that I'm going to give you. So hopefully you had a chance to pause the video for a moment, and we're going to look at r of x next. And so it's given us x to the power of 4 minus 5x cubed plus 7x squared minus 2x plus 8. So according to the derivative rules, r prime of x, which sometimes we also write dr over dx instead. Again, both of those notations represent the derivative. Well, according to the rules, we can ignore the pluses and minuses. So we're going to have basically a bunch of terms being subtracted or added from each other, just like we had at the start of the problem, and we find the derivatives individually. So derivative of x to the power of 4 will be 4x cubed, because the 4 comes down to the front, then we subtract 1 from the power. Now for the 5x cubed terms, the 5 is being multiplied by the x cubed, so we ignore the 5 and we just find the derivative of x cubed, which is 3x squared. Similarly again, the 7 is being multiplied with the x squared, so we ignore the 7 and we find the derivative of x squared, which is going to be 2x to the power of 1, or just simply 2x. Next, we have the product of 2 times x. So again, 2 gets ignored, and derivative of x, well, we said earlier that the derivative of x is going to be 1x to the 0, and from now on, I'm not going to do that anymore. I'm just going to write 1 directly and save myself a little bit of time. So for now, I'll just keep it for a moment. but the x to the power of 0 is 1, and 1 times 1 will be 1, so we will not write the x to 0 from this point on. Finally, there's an 8 at the end, and the derivative of 8 is 0 in this case because 8 does not have a variable. It's just a constant all by itself, so it gets derived to 0. And as you can see, we have now the derivative of all the terms that we want, and so we'll just write a clean version of the answer. So the dr over dx, also known as the r prime of x, the derivative, is going to be 4x cubed. There's nothing to do there. The next term, we have to multiply 5 and 3. That's going to give us 15x squared. The next term, we have 7 and 2 being multiplied. That's going to give us 14 with the x. And finally, negative 2, and the rest of it is just zeros. So that's it, and we're done with the problem. Okay, so pause the video and see if you can get the derivative of the third part. Okay, so in this case, we have y equals to 3x to the power of 3 halves minus 7/8 x to the power of 11 plus 6 over 5 x to the power of 1 half, and finally plus 10. So before I can find the derivative in this problem, the x to the power of 1 half is written in the denominator. This is bad. We can't differentiate it when it's on the denominator, so we're going to rewrite the problem first and then proceed to find the derivative. So at this point in time, I'm just rewriting the original problem, so I'm going to keep writing y, not dy prime. And so again, the first few terms don't need to be fixed. They are already good to go. The term that needs to be fixed is the 6 over 5 with x to the power of 1 half. So it used to be 1 half in the denominator. I'm going to bring it to the numerator and make the positive disappear and put a minus instead. So I'm just rewriting it from the denominator to the numerator, and that means I have to change the exponent from positive to negative. And so the rule I'm using here is the rule that tells me if I have 1 over a to the m, that's the same thing as a to the minus m in the numerator. So this is some kind of algebra rule. Maybe you remember it, maybe not, but if you don't remember it, now it's a good time to recall it. And keep in mind that between the 3, the 7/8, the 6/5, there's a lot of multiplication between those numbers and the variables. So those numbers will be ignored. The only one that's going to become 0 is the 10 at the end will become 0 because the derivative of 10 by itself without any variable will just become 0. So we're ready to find the y apostrophe, or the derivative, dy over dx. And so 3 is going to hang out, and we need the derivative of x to the 3 halves. The derivative of x to the 3 halves will be 3 halves x to the 3 halves minus 1, which is the same thing as saying 1 half. So I'm just going to do that right away. And if you don't know how to do it, just use a calculator or go to a scratch paper and do 3 half minus 1. That's the same thing as 3 half minus 2 halves. Since the denominator is the same, all I have to do is subtract the numerators, and I just get 1 half at the end. So that's how you can do that without a calculator in case you don't know. Next, we have the 7/8 and x to the power of 11. Well, 11 comes down, and I subtract 1 from the 11, so now I have x to the power of 10. Next, we have the 6/5, and this one is a little tricky because the exponent is negative, so just pay attention. We drop the power to the front, so negative 1 half in the front, and then we are supposed to subtract 1 from the original power. So this time I have negative half minus 1. So again, that's the same thing as negative half minus 2 over 2, which now they both have the same denominator, so we can write negative 1 minus 2 all divided by 2, which is negative 3 over 2. So instead of writing negative 1 half minus 1, I'm just going to put the answer directly, which is negative 3 halves. And that's the derivative of the third term. And finally, the derivative of 10 is going to be 0. Like we said, 10 doesn't have any variables, so when you differentiate it, it just disappears. Okay, so that's pretty much it. All we have to do now is just clean up the little mess that we've created, and the derivative, which is dy over dx, will be equal to I'm supposed to multiply the 3 with the 3 halves, so when I multiply 3 with 3 halves, the way it works is you multiply the numerator with the numerator and the denominator with the denominator. So the 3 goes with the 3, we get 9/2 x to the 1/2. And so that's it for the first term. The next term, we have 7/8 times 11. And again, I can put 11 over 1 and multiply straight across, top with top, bottom with the bottom. So that's going to be 77 over 8 with x to the power of 10. Next, we have the fraction 6 over 5 multiplied with the fraction negative 1 over 2. And again, you can go straight across, top with top, bottom with bottom, but this time I prefer to do this instead. I'll go ahead and divide the 6 and the 2 by 2 to make the numbers a little bit smaller first, and then I'll multiply straight across. So I'm going to end up with -3 all divided by 5 times 1 is just going to be 5. So -3/5. And x to the power of -3/2 is the second part of that term. And that's it. We are finished with the problem, and we can now move on to the next one. So again, pause the video and see if you can get this done. There's a couple of things here you gotta worry about. The fraction 3 over x is on the denominator, it needs to go away. And this guy right here, the cube root of x squared, needs to be rewritten as a power, as an exponent, so you can differentiate. Okay, so as we said, let's start by rewriting. So the 2x cubed is not a problem. We're just going to write it down and leave it alone. The 3 over x, well, x has power 1 in the denominator, so I'm going to remove it from the denominator and put it in the numerator and give it a negative exponent. So it used to be 1, now it's -1. And finally, there's the cube root of x squared. That's the same thing as x to the power of 2/3. And so that's how you rewrite the radical. The square root or the cube roots gets rewritten as an exponent with a fraction. And this is a rule that we've mentioned before, but in case you don't remember it, the nth root of a to the m is the same thing as a m over n. This is, again, one of the algebra rules we've mentioned before in this course, but in case you don't remember it, there it is. That's the rule I used to rewrite the last portion of this problem. And so now I'm ready to find y prime, or dy over dx, the derivative. And as we said previously, the product of 2 and the x, the cube, and the 3 and the x to the -1, those 2's and 3's are going to be ignored because they're just a product of 2 and a variable. We just worry about the variable. So x cubed becomes 3x squared. The 3 is hanging out. The x to the power of -1, we bring the exponent down, then we subtract 1 from the existing power. So it's going to be -1 and then -1 again, which is the same thing as saying -2. I'll just write that instead. And finally, derivative of x to the 2/3, that's 2/3 x to the power of -1/3. Where did the -1/3 come from? Well, 2/3 minus 1, that's the same thing as 2/3 minus 3/3. They have the same denominator, so now we just do 2 minus 3, which is -1 all divided by 3. So that's how the -1/3 came about. Okay, we're almost done. We just have to clean up, and so let's write down the final answer. The derivative, which is y prime, or dy over dx, is 6x squared plus 3x to the power of -2, and then plus 2/3 x to the -1/3. Now, if you're wondering whether you need to have a negative exponent or positive exponents or whatever, it doesn't really matter for now. We're just practicing how to find derivatives. Later on, depending on the next question that we have to answer, we'll worry about modifying these terms with the negative exponents. Sometimes it's beneficial to rewrite the problem with positive exponents. Sometimes it doesn't matter. So for now, we'll just leave it as is. I also want to mention something here before we move on. Please always make sure you label everything. You need to know which function is the original function, which one is the y function, which one is the derivative of y, because later on we will not be stopping at the first derivative. We're going to find more derivatives for the same function. So we're going to take this answer that we put in a box and we're going to differentiate it again. And we want to be able to distinguish what each function is, right? Is it the original one, or is it derivative, or is it the derivative of the derivative? Because each one of them will have a different goal or a different job to do for us in the problem. So please get into the habit of writing down the label of everything, right? A lot of people will just start writing 2x cubed, and then they forget whether that one is the original function or the derivative. But if I label it, then there's no mistaking this. The first two are just the original problem rewritten, and the bottom two are the derivative of what is given to me. Okay, the last part of this problem before we move on to the more complicated scenarios. So pause the video, and this time we have w's instead of x's or t's or whatever. It doesn't really matter. It's just a random variable. We treat it the same way. Okay, so hopefully you had some time to think about this. And again, I need to worry about a couple of things. This w is inside of the square root. I don't like that. And this w over here is kind of like on top of a fraction. That's not too big of a deal. We'll rewrite it. And finally, this one, w cubed, is on the denominator. We cannot differentiate a problem when the w is on the denominator. We don't have the tools yet to do that, so we'll have to rewrite the problem. So anyway, there's like basically three things that we need to fix. First, the square root, we can rewrite it as w to the 1/2. That's because there's an invisible 1 and invisible 2 everywhere that we don't write. And keep in mind that 4 is being multiplied by all that. Next, we have the 5 over w cubed. That's the same thing as 5w to the power of -3. We can rewrite the w that was in the denominator on the numerator, but we just have to give it a negative exponent. And the last term, just to be consistent, I'll write 1/5 and w next to it. So instead of putting the w on the numerator and confusing myself about what's the number, what's the variable, I'll just write it on the side, and this makes it a little bit easier to see what's going on. We have basically three terms with a constant times a variable. So for this problem, we are going to ignore the 4, 5, and 1/5 for a little while, just worry about the variables. So I'm looking for the derivative. So first I can write f prime of w, or I can write df over dw. So that's how we refer to derivative in this case, either using the apostrophe, or we can write df over dw. F is the name of the function, that's why it goes on the numerator, and the independent variable is the guy inside the parentheses, or the letter that I see repeating multiple times over here on the side, that goes in the denominator. And the d's just refer to the fact we're finding derivatives. So 4 is going to hang out. We differentiate the w to the 1/2. It becomes 1/2 w to the -1/2. Let's pause for a second. Where did this -1/2 come from? The original number was 1/2, and the derivative tells me to subtract 1. So that's going to be 1/2 minus the same thing as 2 over 2, which is -1. Sorry, let's just do it the long way. 1 minus 2 over 2, which is -1/2. So that's how I'm getting the -1/2 for the first fraction, or for the first power. Next, we have a -5. It's being multiplied by some random stuff, so we're just going to ignore the 5 for a moment and bring the power down. That's -3. And the w has -3 already, and we're going to subtract 1 from that. So -3, -1, the total will be -4. I'll just write down -4 instantly. That way we can save a little bit of time. And finally, the 1/5 derivative of w. Derivative of w is just going to be 1. We've mentioned before that if you have x or w or t or whatever, their derivative is just going to be 1. And again, why is that? That's because this variable w has power 1. So when I differentiate it, the power comes down to the front, and then I lose 1 from the original power. And 1 minus 1 is going to be 0, but w to 0 is really 1. And so 1 times 1 is going to be 1, and that's why I'm seeing 1 there. So that's how that one is obtained. I'll just keep this here so that we can see it in case you want to reference this later on. But that's how we're getting the 1. Okay, the last thing we have to do is just clean up the mess and multiply the numbers on the outside. So I'll write fw prime, or the derivative of f, which is the same thing as df over dw. Well, 4 times half, when I go straight across, multiply 4 with 1 and 2 times 1, I'm going to get 4 over 2, which is the same thing as 2. And another way I could have done this is I could have divided the 4 and the 2 by 2. That gives me 1 and 2. And so the result is the same. 2 times 1 over 1 is just going to be 2. So regardless of how you get it done, the answer is going to be 2, w to the negative half. Then we have negative 5 times negative 3. That's going to be positive 15. And I don't do this again. I don't multiply the 5 with the w because the 3 and the w were being multiplied. So all I have to do is just give the 5 to one of them, either the 3 or the w. So w hangs out. And finally, plus 1/5 times 1 is just 1/5. So that's the final answer in this case. So this is how you apply the basic the basic differentiation rules. And again, a recap of what we just did is on the first page. These are the basic rules that we're applying. So it's a really, really good idea for you to try to memorize these rules and know how they work. Now notice that none of these rules tells me what to do when I have x in the denominator or a variable in the denominator. Later on, we'll see something like the quotient rule that will be able to handle this. But for now, if I see x's on the denominator, I have to find a way to put them in the numerator. So if my variable is found on the denominator and I'm trying to use one of the basic rules, it won't work. I'll have to rewrite the problem with x on the numerator. And I believe that's what we're going to be dealing with in the next problem. So in this problem, example 2, we have some variables in the denominator and we have to deal with that. So for the problem number 2, it says find the derivative again, but this time the expressions given to us are slightly more complicated. This one is g of t, and it has a fraction with t's on the numerator and t's on the denominator. So for a problem such as this one, where we have a single term on the denominator, this is just one term because there's only one letter there, the way it's going to work is we're going to rewrite the problem by giving that term on the denominator to everyone in the numerator. So what do I mean by that? I mean the 5t cubed that was already there will get its own fraction, and it will have t squared on the denominator. And same thing with the 4 square root of t, we'll give it its own denominator. And hopefully, what we can do next is reduce the fractions to the lowest terms, and maybe the t will disappear from the denominator. But if it doesn't, then we'll have to worry about what to do again. Now, one thing I want to do right off the bat is the square root of t, I'm going to rewrite it as t to the 1/2 this time. And that's because I want to save myself a little bit of work. It's helpful to rewrite it as an exponent because then I can worry about what to do with each fraction because they both have t's on the numerator and the denominator. And I'm about to use a rule from algebra that says a to the m divided by a to the n is a to the m minus n. So if I have the same base on the numerator and denominator with different exponents on the numerator and denominator, the rule tells me to subtract the numerator exponent minus the denominator exponent. So I'm going to basically apply this twice. One time for the t cubed over t squared, and one time for the t to the 1/2 divided by the t squared. So starting with the t cubed over t squared, that's the same thing as t cubed minus 2. So the exponent power goes first, the power of the numerator goes first, and then the power of the denominator goes there, and 3 minus 2 is just 1. So the g of t in my problem is 5t to the power of 1 minus, I've got 4t to the 1/2 and then t to the power of 2. So let's see, t to the 1/2 divided by t squared. According to the rule, the exponent of the numerator goes first and then the exponent of the denominator. So numerator has 1/2 power, so we put it first. Denominator has 2 power, we put it next. And 1/2 minus 2, I hope you already know by now, it's negative 3/2. So these are all basically kind of reminders about how to deal with fractions from algebra courses. It's helpful if you know them, and if you don't, well, this is your chance to kind of catch up and remember how to deal with these scenarios. And remember, this is not even the derivative yet. This is still the original problem, just being rewritten in a way that allows me to use the basic differentiation rules. So now that I've rewritten the problem in a way I can use the derivatives, we will start by finding g prime of t, also known as dg over dt. So first things first, we've got the 5t in the front. 5 is being multiplied with the t, so the 5 goes for the ride, and we just differentiate the t. T is like a w or like an x. The derivative of w or x is just 1. And the same way, the derivative of t is going to be 1. Similarly, the 4 is going to hang out and wait for its turn, and we just need to worry about the t to the negative 3/2. So the power comes down according to my rules, and then I subtract 1 from the existing power. So it used to be negative 3/2, and I'm subtracting 1. That's the same thing as saying negative 3/2 minus 2 over 2. And hopefully you can recognize that this is negative 5/2, which is the new exponent in my problem. I'll keep this here so you can see where that exponent came from, but that's how it's done. All right, lastly, we'll clean up this massive mess we've created. So the derivative of g with respect to t is going to be 5 times 1 is just 5, and then 4 is negative, the 3/2 is negative, so double negatives is going to make a positive. And now I got to worry about the 4 being multiplied with the 3/2, 4 times 3 over 2. That's the same thing like 4 over 1 times 3 over 2. So you can either go across, that's going to be 12 over 2, which is 6, or the other option is to first reduce it to the lowest terms, so divide the 4 and the 2 by 2, we get 2 and 1, and then you multiply straight across whatever remains. 2 times 3 is 6, and 1 times 1 is going to be 1. We get 6 over 1, which is ultimately just simply 6. So regardless of how you do it, the answer should be 6 in the front as the constant, and it's being multiplied with the t to the power of negative 5/2. And now we are completely done with this answer. Okay, last but not least, we have part 2 of this problem. We have the function called m, and the variable they're using is v. So m of v in this problem is 7v plus 3 multiplied with v squared minus 9. So unfortunately, again, I don't have a rule that tells me what to do when I have a sum of terms being multiplied by a difference of terms. In the next few pages, we will see something called the product rule that will help us out, but for now, we don't have such a rule. So for now, the only choice for me is to FOIL the terms first, so multiply everybody out, and then take the derivative of the answer. So I'm going to start by doing that. So 7v times v squared is going to be 7v cubed. Then I have to worry about the 7v multiplied with the negative 9. So the 7 is positive, the 9 is negative, so we're going to have negative 63v. Next, we have the 3 multiplied with the v squared. That's going to be 3v squared. And finally, 3 times negative 9. The 3 is positive, the 9 is negative, so the answer is going to be negative and 27. There are no like terms to add or subtract, so I can pause here and start by asking, okay, what's the derivative going to be? So the dm over dv, that's the derivative of the function m with respect to v. And just like before, we're going to use the basic 4 rules. Keep in mind 7 is being multiplied with the v cubed, the 63 is being multiplied with the v, the 3 is multiplied with the v squared. And so ignore the 7 and just differentiate the v cubed. That's 3v squared. Next, we ignore the 63. We differentiate the v, which is just 1. Next, we ignore the 3. We differentiate the v squared. That's going to be 2v. And finally, the 27, the derivative of that is going to be 0 because 27 here does not have any variables. So its derivative is 0. And so we're basically done. All we have to do is now clean up the mess a little bit and multiply the 7 and the 3. We get 21v squared. If I multiply the 63 and the 1, it's going to be 63. And if I multiply the 3 and the 2v, it's going to be 6v. Now, usually what we like to do is put the highest power first, then the next power, then the number. So if you want to do that, you would write basically 21v squared plus 6v minus 63. So that's the slightly nicer way of writing down the answer. This is what we call the standard form because the highest power is first, then the v with the smaller power goes next, then finally the constant that doesn't have any v's is written at the end. This is just known as the standard form, and it's kind of pretty. That's why we like using it. It's useful when you're doing things like factoring. So I'm going to leave it in the standard form. So far, we've done every single problem using the basic rules of differentiation, but what if it was very difficult for me to FOIL something like this? Or what if it was not possible to divide out the fraction like we did on part one? What if I had two terms in the denominator? If I had two terms in the denominator, this technique would not have worked. Well, I still want the derivative, and the basic rules don't help me. Well, that's the point of what we're about to learn next, which is the quotient and the product rules. So these product and quotient rules are useful because they will allow me to find the derivative without having to FOIL first or divide the terms first. So this basically says if I have a product of function times a second function, then according to the product rule, what I have to do is basically take turns differentiating the functions. So first differentiate the f, leaving the g alone. Then when you're done, differentiate the g, leaving the f alone. And when you're done, you just add the solutions that you got. So it's like taking turns. The f takes a turn, then the g takes a turn. When you're differentiating one function, you leave the second component undivided, or undifferentiated rather. So how would that work in an actual problem? Let's look at example number 3. So in example number 3, this is the same one we just did. I'm going to repeat it, but this time I'm going to use the product rule rather than FOIL everything and use the basic rules. So if I want to apply the product rule for this problem, the first thing I want to start by doing is labeling each one of these things as f and g. So I'm going to color code them so you can see what I'm doing. So first, I find where the product is. The product is right in the middle. And so the first half of the problem gets called f. The second half of the problem gets called g. And I'll make a short, small table on the side describing what f is in my problem. And f in this problem is 7v plus 3. And then I'll write down what g is in my problem. The g is v squared minus 9. So what I'll do is, on the same scratch paper, I'll find the derivatives of f and g as preparation. So this is not part of the problem. This is kind of like just me doing my own thing on the scratch paper. I'm going to ask myself, what's the derivative of 7v plus 3? And I'll write it over here on the side for a moment. So derivative of 7v plus 3 is just going to be 7 times 1 plus 0, which is the same thing as 7. So for now, I'll just worry about 7. Same thing again with the v squared minus 9. What's the derivative of v squared minus 9? I'll write it off to the side. The derivative of v squared is going to be 2v. Derivative of 9 is 0. Sorry, derivative of 9 is 0 because 9 doesn't have any letters. And that's the same thing like 2v. And that's the thing I will worry about. That's the thing I will keep in my mind. Now, once you've done this on scratch paper, here's what I want you to do. I want you to multiply the corners of this little rectangle that you just made. So the important thing here, if you want to use my little trick, is you want to put f and g in the first column and their derivatives in the second column. And if you do this, then all you have to do now is multiply the corners f prime g, because that's what the rule tells me to do first. Multiply f prime and g. Then, when I'm finished, multiply the other two corners, g prime and f. That's what this other half of the theorem tells me to do. And on the way there, just add in the middle. So what would that look like? So I'm looking for the m prime of v. So I want the derivative of the function m with respect to v. So the rule basically tells me to multiply these first two corners first. So I multiply the 7 with the v squared minus 9. Then the rule tells me to put a plus sign. That's why I wrote the little plus inside my little arrow. And notice how I didn't do this. I put an actual direction on my arrow. So I start here and I go around and I end with f. And along the way, I'm supposed to add. That's where the addition comes from. Right? That's this plus sign here. I put it in the middle. And then on the way back, when I turn around, I'm supposed to multiply the 2v and the 7v plus 3. Doesn't matter what order you put them in. You can put the 2v first and the 7v plus 3 after, or you can put the 7v plus 3 first and then the 2v at the end. The multiplication is commutative, so it doesn't matter what order you put them in. You can write it however you please. But the bottom line is we just did exactly what the product rule told us to do. We put f prime, we put g, we put f, and then g prime again. So this is almost the end, except I want to convince you that this is equal to what we did before on the previous page. So I'm going to FOIL everything out now and combine like terms. Normally, we would not do that, but I want to convince you that this answer that we got is the same one on the previous page. So let's continue and FOIL. 7v squared, 7 times 9 is 63. 2v times 7v is going to be 14v squared. And finally, 2v times 3 is going to be just positive 6v. If I combine like terms, there's only two that can be added here, which are the 7v squared and the 14. That gives me my derivative, dm over dv, which is the same thing as the apostrophe of m, meaning the derivative of m. Well, it's going to be 21v squared and 6v and negative 63 at the end. So let's just compare this answer to the one we had on the previous page. So we have 21v squared plus 6v minus 63, and we have the same solution over here. Obviously, it's the same problem. Regardless of how you find the derivative, you should get the same answer for the derivative. The difference between this one over here on this page is I FOILed first and differentiated, whereas on this page here, I differentiated first, then I FOILed. Now, it turns out that this method here is actually a lot better in general than the previous method that we showed on the previous page. A lot of times it's not possible to FOIL these things here, so this is the only way to do the problem. Now, this part of the problem where I have the colors is not required. Later on, we'll start mentally just doing it in our head. But for now, I'll keep writing it down for the next couple of problems so you can kind of see what is happening in my problem. Now, the quotient rule is pretty much very similar. The setup that I'm going to do is very, very similar, except instead of a plus sign, I'm going to be putting a minus, right? The difference between the product rule and the quotient rule is that we have a minus, and also we have an extra denominator that we have to worry about. But the numerator of the fraction is almost like the product rule. So if you follow my setup, if you set it up always the right way, then you will never get these problems wrong. It's going to work itself out. And even if you didn't have the rule memorized, you're still going to get the right answer, as long as you know how to set it up and you can follow the little direction of the arrow. So let's see what's happening with p of x. So p of x has a fraction with the 5x plus 7 on the numerator, and it's being divided by 3x minus 4. Unfortunately, the denominator is not one term. This has two terms. So these things on the denominator are two terms, so I cannot separate the fraction and reduce it to lowest terms. It will not work. What I have to do instead is use the quotient rule, this new rule that tells us what to do if we have variables on the numerator and variables on the denominator. Just like before, something will be called f, something will be called g. The f is always the things in the numerator. So 5x plus 7 is my f portion, and the denominator is going to be called g for us. And once you do that, I want you to put another column and find the derivative of f and the derivative of g on the side. So what's the derivative of 5x plus 7? Put that answer onto the side. Derivative of 5x is just going to be 5 times 1. Derivative of 7 is going to be 0. That's the basic rules of differentiation. The total here is just 5, and 5 is what I need to worry about and carry for the future. Okay, same thing again with the 3x minus 4. What's the derivative of 3x minus 4? That's going to be 3 times 1 minus 0. The root of 4 is just basically 0. And that's the same thing as 3. So 3 is what I care about for the rest of the problem. So again, because I'm going to be using the quotient rule, because I have a fraction in this problem, I'll start with the f prime and I'll multiply some things out. So multiply these corners, f prime and g, then multiply these corners, g prime and f. But this time I'm going to be subtracting because I'm applying the quotient rule. So p prime of x, meaning the derivative of p with respect to x. It's going to be a fraction, a really, really big fraction with a numerator and denominator. So what's on the numerator? On the numerator, I'm going to be writing down 5 times 3x minus 4. Okay, so the 5 from this corner gets multiplied with the 3x minus 4 from the opposite corner. And you always have to follow that order. You have to multiply these two corners first, otherwise it's going to be wrong, because in this case we will be subtracting, and if you don't do the subtraction in the right order, you're going to get the wrong answer. Once you've done that, you're going to multiply the 3 from this corner with the 5x plus 7 from the opposite corner. So 5x plus 7 goes in the opposite corner, so we multiply it with the 3. And the last thing we have to do, because this is a quotient rule, is take the original denominator, which was 3x minus 4, that's the original denominator, and we're going to square it. That's always what's going to happen when you're dealing with a quotient rule. So it's basically the derivative of the numerator is low d high minus high d low, and then you're supposed to square the bottom and off you go. So you differentiate the numerator, then you leave the denominator alone. Then you differentiate the denominator and you leave the numerator alone. And you're supposed to subtract all those things. Then you square the bottom and off you go. You're done with the problem. So technically this is the answer, but I'm going to spend a little bit of time here to clean it up a little bit. So p prime of x is going to be, in this case, 5 times 3x minus 4. 5 times 3 is going to be 15x. 5 times 4 is going to be negative 20. And then again, negative 3 times 5x is going to be negative 15x. And negative 3 times 7 is going to be negative 21. All divided by that same denominator, 3x minus 4, everybody squared. I'm noticing here something special. The 15x minus 15x are supposed to be canceling out. They undo each other. And the only thing that remains is negative 20 and negative 21. They're both negative, so I'm just going to combine them and get negative 41 instead. So the answer is negative 41 divided by 3x minus 4, everyone squared. Okay, example 4 gives us more of the same thing. We are supposed to find the derivative again in simplest form, and what I want to point out here is, again, the denominator has more than one term, so I cannot reduce the fraction and do the basic rules. I have to start with the quotient rule. And so, again, let's start by writing the v of t in this case. So it's a fraction, so I'm going to use the quotient rule. I've got some stuff in the numerator, and I've got some more things in the denominator. So what I want to do first is start by labeling my numerator and denominator. So the numerator is going to be 4 plus 3t plus t squared, and I'll need its derivative on the sides. So let's see, derivative of 4 is going to be 0, derivative of 3t is just 3, and derivative of t squared is just 2t. And you know what? Let's write it like 2t plus 3. It's a little bit prettier, and it's a little bit more manageable. So that's the numerator's derivative, and next I'll need the derivative of the denominator. So first let's write down the denominator, the t cubed plus 5. Its derivative is going to be 3t squared plus 0, which is the same thing as 3t squared. Because the root of 5 is basically 0, I'm not going to write it down. This is a quotient rule, so I'm starting with f prime and I'm going around multiplying some corners with a minus sign in the middle because I'm doing a quotient rule. So in this case, I'm going to write down v prime of t or dv over dt. This is the notation for the derivative. It's some kind of a fraction. And what goes on the numerator is the 2t is going to be multiplied with the t cubed plus 5 first. So let's go ahead and record that. So the 2t plus 3 gets multiplied with the t cubed plus 5. And let me color code them so you can see which one came from where. And next, there's a minus sign because the rule tells me to put a minus. I'm doing a quotient rule. And then I'm supposed to multiply the 3t squared with the opposite corner. So 3t squared gets multiplied with the 4 plus 3t plus t squared. That's the last corner of f. Now all this is we have a song for this. It's low d high minus high d low. When I say low d high and high d low, the d stands for derivative. So low d high d low, square the bottom. So I'm about to square the bottom, which is the t cubed plus 5. And off you go. So once you square the denominator, that's it. You've done your quotient rule. I think I'm going to need more space, so let me shrink all this down a little bit so we can fit more things on this page. So these are the components that I need on a scratch paper, but this is the actual answer down here. So believe it or not, from this point on, it's just basically algebra. All we have to do is FOIL everything out, add like terms and so on. But this is the end of the calculus part, right? The calculus itself is not very difficult. It's the algebra that's usually going to get you here. So be careful with FOILing everything out and combining like terms correctly. My numerator is going to be massive, so let me make a really big fraction here. And so let's begin by FOILing everybody. So 2t times t cubed is going to be 2t to the power of 4. Then 2t times 5. That's going to be 10t. Next, I have to worry about the 3 and the t cubed. That's going to be 3t cubed. And finally, 3 with the 5 is going to be 15. For the next portion, I'm going to pretend like negative 3t squared is all one component and multiply it 3 times with the 4, with the 3t, and with the 3t squared. So I'm going to get 3 different negative answers, starting with 12t squared, because 3 times 4 is 12. Then the 3 gets multiplied with the 3, we get negative 9. T squared times t is going to be t cubed. And finally, negative 3t squared times t squared is t to the power of 4. So by the way, when I multiply t squared times t, how am I getting t cubed? It's because the bases are the same, so I just add 2 plus 1 and I get the 3. So when I did like 3t squared times t squared, I had t squared twice. So t is in the base, and then 2 plus 2 is 4. That's how I'm getting this exponent and this exponent and this exponent and so on. Okay, the denominator, we always leave it alone. We don't touch it. We just copy it and we continue. So if I look at the numerator, I need to check if there's any like terms. I'm seeing 2t4 and another t4 term, so those can be placed together. We can combine those terms, they're like terms. I'm also seeing that there's a t cubed here and another t cubed there. We can add those terms together, and nothing else can be added because the rest of the terms either have t or t squared or no variables at all. So the v prime, or the derivative of the function v with respect to t, the independent variable, well, let's see. 2t4 minus t4 minus 3t4 is going to be negative t4 because 2 minus 3 is negative 1. So that takes care of these two terms. Next, I have the t cubed. So I'm going to do negative 6t cubed because 3 minus 9 is negative 6. And notice what I'm doing. I'm always doing it in standard form. So I'm starting with the highest powers first, then I go down to the next one, and so on and so forth. That's why I start with the t fourth, then the t cubed. Now I'm looking at the t squareds. I'm checking to see there's only one t squared terms. Everything else doesn't have t squareds. So I write that one next. Next, I'm going to write the term that has the t, which is the 10t. And finally, the term that doesn't have any variables, that's the 15. And it's all being divided by t cubed plus 5 all the way to the power of 2. And that's how you can finish this problem. And actually, this is the end. There's nothing we could add or subtract anymore, so this is it. Okay, last we have the p of x polynomial. And again, we've got two choices. We can either FOIL first and use the basic rules of differentiation, or we can use this new product rule. I'm going to use the product rule here just so we can get some practice with the product rule. So I'm going to write the original problem first. And the reason why I'm writing it down always, even though it's like right here, I can see it next to my own notation. When I'm writing it down, I'm kind of thinking to myself, what am I supposed to be doing? I'm basically making this multiplication sign visible. This tells me that I have a product in my problem, so maybe I want to use the product rule. So when I'm writing it down, I'm kind of analyzing it and trying to decide what's f, what's g, and so on. So in this case, f is the 4 square root of x plus 3. I'll need its derivative on the side. The g in this problem is going to be 2x minus 5, and I'll need its derivative on the side. And this one is a product rule, not a quotient rule. So when I do things, when I multiply things out, I'm going to be putting a plus, not a minus, because of the product rule. Keep in mind that 4 with the square root of x, that's the same thing as 4x to the 1/2. So it's helpful to rewrite it like this so that we can differentiate it quickly later on. And speaking of which, what's the root of 4x to the 1/2 plus 3? So the 4 is going to hang out and wait for its turn. The x to the 1/2 becomes 1/2 x to the negative half. And the root of 3 is going to be 0. I'm not going to even bother it with it. Now 4 times half is basically 4 over 2, which is 2. And x is just going to be hanging out. So my final answer was 2x to the negative 1/2. Now for g, what's the derivative of 2x minus 5? The derivative is 2 times the derivative of x, which is 1, and 2 times 1 is just 2, minus the derivative of 5, which is 0. So 2 minus 0 is just 2, and I'm just going to write down the 2 and not worry about anything else. So this stuff that I'm writing, for now, I'm going to keep writing it, but later on, I'm going to start skipping it and just doing it mentally. And it's probably a good idea for you to keep writing it down because you're still at the early stages of finding derivatives, so it's helpful to see everything on the page in front of you. But anyway, I've color-coded everything, and now I'm looking for the derivative of p, which is p prime of x. This is dp over dx, the derivative. And this is not a quotient rule, so don't worry about putting a fraction. We're just going to multiply the 2x to the negative half with the 2x minus 5, then put a plus sign, then put a 2, multiply with 4x to the 1/2 plus 3. So remember, multiply these corners first, then multiply these corners afterwards. It's kind of like an x. If you're writing it correctly, you will never get it wrong. And just so we're clear on the colors, this is the f prime, this is the g, and then the rule tells me to do g prime times the function f. And in the middle, I'm supposed to put a plus sign. So technically, this is the end of the calculus. What I have to do next is clean up this massive product and sum that I have. So let's FOIL everything out or distribute and add like terms if there's any. So 2x to the negative half gets multiplied with the 2x, then gets multiplied with the 5. The plus 2 gets multiplied with the 4x to the 1/2, then with the 3. So let's start with the first part. Remember, when your bases are the same, your powers get added. So first, 2 times 2 is going to be 4. Then I have x to the negative half with x to the power of 1. So x to the negative half gets multiplied by x to the 1. I'm supposed to add the exponents because the bases are the same. So I get negative half plus 1, which is the same thing as just simply x to the 1/2. Next, negative 2x to the negative 1/2 gets multiplied with the negative 5. The result is negative 10, and the x doesn't have any friends, so we just write x to the negative 1/2. Next, we have the 2. times 4x to the 1/2. So 3 times 4 is going to be 8, and x is just going to hang out. And lastly, 2 times the 3 is going to be 6. Okay, so pretty much done almost. We just have to worry about any like terms that are still in the problem. So any like terms, well, I'm seeing 4x to the 1/2 and 8x to the 1/2. They both have x to the 1/2. Unfortunately, the middle term has x to the power of negative half, so it can't be added to those two. Well, we'll just worry about adding the first and third term then. So 4x to the 1/2 and 8x to the 1/2. In this case, we just add the 4 and the 8 to get 12, and x to the 1/2 is just going to chill next to them. And next we have the 10x to the negative 1/2, and finally the plus 6 at the very, very end. So this is the derivative of my function p. So earlier in this video, I mentioned that you want to label everything. You want to write y and y prime and so on. Well, that's because we are sometimes interested in higher order derivatives. So for example, if you're working with a projectile, you want to know the distance, the speed, the acceleration, and that requires different types of derivatives. So first derivative, second derivative, at least. So what do I mean when I say higher order derivatives? I just mean that we want the derivative of a derivative. So we know already how to find the first derivative. It's y prime, y apostrophe, also known as dy over dx, for example. The second derivative gets two apostrophes, or d2y over dx2. So what exactly is the second derivative? Well, if I have a function, let's say y is x cubed, then its derivative, y prime, is going to be 3x squared. Somebody could say, I want you to differentiate 3x squared. If I did, I would end up with 3 times 2x, because the derivative of x squared is 2x. By the way, that's just the same thing as 6x. And what would I write next to it? How would I label it? I would label it as y double prime, y double apostrophes. It's the second derivative of the thing that I started with, which was 3x. X cubed. So it's the derivative of the derivative, basically. That's what we mean with the second derivative. Now, somebody can say, I want you to find the derivative of 6x. What would that be? Well, the derivative of 6x would be 3 apostrophes y triple prime, or the third derivative, and it would just be simply x. And somebody could say, I want the derivative of 6. And, well, what would that be? Well, it will be 4 apostrophes. Now, once you have four apostrophe, or like even 3 or more, it becomes really tedious and really annoying to have to write all these apostrophes. So instead, we write 4 inside parentheses. Or instead of 3 apostrophes, we write 3 inside parentheses. That's the notation when you have a high order derivative. Even actually on the 2 apostrophes, you can write 2 inside parentheses, not y squared. So there's a difference between writing y2 and y2 inside parentheses. In math, we treat this y squared as if it's multiplying the original problem by itself twice, whereas we think of y with the 2 inside parentheses as being the second derivative. So it's the derivative of the derivative. But anyway, back to this original problem. If I want the fourth derivative, that just means find the derivative of 6, which is just simply 0. So at this point, any other derivative you do after this will be also 0. So this is what we mean when we say we want higher order derivatives. It just means take the derivative of your answer. And so if you want the third derivative, you need to know the first derivative and second derivative, and then differentiate them to get the fourth one. And the notation is, as usual, apostrophes, or like I said, we now can put parentheses around the numbers, and that will be the derivative. So let's practice doing that with example number 5. So in example number 5, we're given some kind of function, and we're being asked to find first dy over dx, meaning the first derivative, and then d2y and dx2. This means the second derivative. So we want the derivative of the derivative. So first I'm going to be getting the derivative and writing it here, and it's going to give me some answer that I'll put a box around. For part 2 of the problem, I'll need its derivative. Whatever I put in the box, I'll need its derivative. So let's begin with part 1. So the function is giving me 5x fourth minus 3 over square root of x plus a 7. as we mentioned before, it's not helpful to have the square root of x on the denominator, even though now I have a quotient rule that can work it out. The quotient rule is really annoying and really difficult to use, so we'll try to avoid it by rewriting the problem with a power instead. So instead of x to the 1/2 on the denominator, because that's what really is, the square root of x, I'll write x to the -1/2 in the numerator. So again, 1 over square root of x, that's like the same thing as 1 over x to the 1/2 on the denominator, or just simply x to the -1/2 in the numerator. So that's how I'm dealing with this square root thing. And keep in mind, this is the original problem, so now let's look for the derivative. So dy over dx, also known as y with a single apostrophe. So y prime, or the first derivative. What's the derivative of 5x for? Well, it's going to be 20x cubed. Then I need the derivative of 3x to the -1/2. So the -3 in front is going to get multiplied with the -1/2. It's going to give me 3/2 with x to the power of -1/2, and I'm supposed to subtract 1. And when I subtract those powers, really I get -3/2. And finally, the derivative of 7 is just going to be 0. I'm not going to even bother writing it down. So I started with 3 terms, and I ended up with 2 terms. The derivative of the first term was this 20x cubed, and derivative of the 3 with the square root of x underneath it turned out to be this complicated 3/2 x to the -3/2. So this is it. Actually, we are finished here. That's the first derivative. So you can put a box around this whole thing and you'll be done. So now for part 2, it's saying we want d2y over dx2. That's the notation for the second derivative. So how do I get the second derivative? Well, I start with the first derivative. My first derivative was 20x cubed plus 3/2 x to the -3/2. And since I want the double apostrophe answer, meaning the second derivative, notation is d2y over dx2. All I do is take the derivative of the answer that I have. So the difference here between this problem and the ones we've dealt with so far, in the problems we've dealt so far, I give you something and I say, tell me the derivative. Whereas now, the problem you're beginning with is something you yourself had to create first. Anyway, it's the same as before. The derivative of 20x cubed, 20 goes for the right, the derivative of x cubed is 3x squared. Next, I need to find the derivative of 3/2 with x to the -3/2. The 3/2 is just going to hang out, and the derivative of x to the -3/2, we bring the power down, then we subtract 1 from the existing power. By the way, -3/2 minus 1, that's the same thing as subtracting 2 over 2. The total is -5/2. So you know what? Let's just write -5/2 right away. And that's the end, technically, except we want to make it look pretty. So we're going to continue writing y double apostrophe or y double prime or the second derivative, which has a different notation, d2y over dx2. Notice how these squares, the numerator one goes between the d and the y, but the denominator one goes at the very end. So that's the notation we use for the second derivative. It has a real reason, but you don't need to get into it right now. Just know that that's how it's written. Anyway, the 20 times 3 is going to be 60 with the x squared. Then 3/2 with the -3/2, we multiply those to get -9/4, and x has power -5/2. And that's the end. So it's not terribly difficult. It's just a little bit weird because you have to create the expression that you need to differentiate first, but that's how you do this. Okay, in example 6, we are going to want the P43. So what is P43? That just means the fourth derivative. And by the way, I should have written, not this notation, I should have written P4 with parentheses 3. If I don't put the parentheses there, like I did accidentally in this case, that just means multiply this guy by itself 4 times. I really want the derivative, so I will add the parentheses here, but that's what I want. So we want to find P4 of t. So that means we are going to start with P of t, and to be as organized as possible, I'm going to make a massive column and kind of keep track of everything that way. So I'll space them out, and I'll start with the P prime of t. I won't use a lot of notation here, so we can make it all fit. But for the first derivative, just differentiate everything that's given. And once you're done, you'll need the second derivative, P2. Then you'll need the third derivative. That's 3 apostrophes, but now it becomes tedious to write that many apostrophes, so I'll put P with the 3 inside parentheses. And finally, the one that they're asking for, the fourth derivative. So I'll write the derivatives of everybody in the same column. So what's the derivative of 8t cubed? 8 hangs out, the t cubed becomes 3t squared, but 8 times 3 is going to be 24, and then the t squared is hanging out next to it. Okay, so what about the 4t squared? What's the derivative of 4t squared? Well, 4 is going to hang out, and the derivative of t squared is going to be 2t. But 4 times 2 is really 8, so I'll just put 8t there. What about the 2t? Derivative of 2t, the 2 is going to hang out, and the derivative of t is 1, but 2 times 1 is just 2. And finally, derivative of 1 is going to be 0, and you don't have to write down the 0. Okay, so that's the first derivative. So you can put a box around it, really, but that's not the answer they're looking for, so let's not box it up yet. Okay, now I need the P double prime, so P2 apostrophes. By the way, if you don't want to write apostrophes, you can put 2 inside parentheses. That means the same thing as the second derivative. So it's the derivative of what you just wrote, basically. So you continue. What's the derivative of 24t squared? Well, 24 is going to hang out, and the t squared becomes 2t. But that's really 48t. Same thing again. What's the derivative of 8t? Between 8 and t, there's nothing except multiplication. So 8 hangs out, and we differentiate t. It's like differentiating x or w or r or whatever. The answer is 1. But really, 8 times 1 is just 8. So let's just write down 8 there. And derivative of 2 is 0. So I don't have to write it. So we started with 4 terms, and now we're back to basically the second derivative has only 2 terms, which is amazing. And let's keep going. So for the third derivative, this is either P3 apostrophes, or sometimes people write D3P over DT cubed. The 3's refer to the fact that we're doing a third derivative. The P on the numerator is the name of the problem. The t in the denominator refers to the fact that we have a lot of t's in this problem. That's the variable we're using for the independent variable. And the d's are just there to remind me that I'm doing a derivative. So that's kind of the notation we use for the derivatives. Anyway, the derivative 48t. Well, 48 has multiplication next to it, and then the t. So we just have to worry about the t itself. The 48 goes for the ride. Derivative of t is 1, and 48 times 1 is really 48. Whereas the derivative of 8 is 0. And again, I'm not going to write it down, so I'm just going to stop there. So far, that's the third derivative, and finally, we get to the fourth derivative. So P4, that's 4 apostrophes. But you can see it's very ugly. That's the reason why we like to write down the P with the exponent 4 like that. So it's a derivative of this derivative, right? Which was the derivative of that one, and that one was the derivative of that one, and that one was the derivative of the original problem. So anyway, derivative 48, well, 48 doesn't have any letters, so the derivative is just going to be 0, and this is the end. So the solution that we're looking for is 0, basically, right? And from this point on, if I ask you what's the derivative of the 0, well, the fifth derivative is 0. What about the sixth derivative? So the sixth derivative, that's the derivative of this guy, which is also 0, and so on and so forth. So forever after, all the derivatives that we can find from this point on are going to be 0. Okay, so we get to example number 7, and this is kind of an application of what we've done so far. In the previous videos in this course, we've had to find equations of tangent lines in the past, and we're going to be repeating this problem throughout the semester. This is one of the main reasons why calculus was created, so don't expect to not have it on an exam or on a quiz. You'll have a lot of these to deal with. The difference is how you find the equation of the tangent line every time. You'll have to find a slope, and the way you find a slope is different every single section. So speaking of which, I want to find the equation of the line tangent to the graph of f of x when x equal to 1. So I've mentioned before, when you hear the words find, equation, and line in the same sentence, you should always begin by writing down the formula, which is y minus y1 equal to m times x minus x1. This is known as the point slope formula. This is your starting point every time you hear the words find and then equation and line together in the same sentence. It's always basically the same. Now, the difference is how you find y1, m, and x1. x1 should always be given to you. That's usually in the question somewhere. So look for the x value that they want, and that's going to be called x1. Now, what about y1 and m? So for y1, the way you find it is you put the given x value into the original function. So whatever my function f of x is, I'm going to put 1 in it. And that's how I get my y1. It's the y-coordinate of the point, basically. And finally, what about m? M is the slope. That's the last thing we need to be able to finish the problem. M is the slope, and the big idea of calculus is that if you want the slope of the line tangent to a curve, so if you hear the word tangent, that means they want you to do some kind of derivative. So in this case, the function is called f, so I need the derivative of f, and then I need to put 1 into the answer. And that's how I get my m value. So put 1 into the derivative. So since I'm going to need the derivative, let's go ahead and look for the derivative here. So on a scratch paper somewhere, you're going to record your f of x function, negative x cubed plus 7x squared plus 5x minus 1. And let's find the f prime. What's the derivative? So when we had to do this problem last time, we had to find the derivative using the limit definition. Now we can avoid the limit definition and just find the derivative term by term using the basic rules of differentiation. Derivative of negative x cubed is negative 3x squared. The power comes down, then we subtract 1 from the power. Derivative of 7x squared. The 7 is going to hang out. Derivative of x squared becomes 2x. And by the way, 7 times 2 is 14, so let's just write 14x. Derivative of 5x is next. The 5 is going to hang out. Derivative of x is 1. And 5 times 1 is really 5, so let's just write down 5 instead. Finally, derivative of 1, or negative 1, is 0, but who cares? We're not going to write it. So this is my function, and this is my derivative. These guys are useful, so make sure you record them somewhere where you can have them handy. The reason why they're useful is because we want y1 next. And so how do you get y1? You put 1 into the original function. So if I put 1 into all the x's, I get negative 1 cubed plus 7 times 1 squared plus 5 times 1 minus 1. So I'm putting 1 into all the places where there was an x, and that's because the given x value is 1. And you'll need your calculator, or if you don't want to use a calculator, it's fine. You can find the answer just by hand. I believe the answer here is supposed to be 16, but let's double check it. So negative 1 cubed is negative 1, 7 times 1 is 7, and 5 times 1 is going to be 5, minus 1 at the end. Okay, so maybe I was off a little bit when I said 16, because I think the answer is supposed to be what? 12. So it seems like the f function evaluated at the point 1 is 12. Actually, it's not 12. It's actually -1 minus 1 is going to be -2. So if 12 is the middle part, and then these two guys right here are -2, 12 minus 2 is going to be 10. So yeah, so the answer is going to be actually 10. So my y1 is equal to 10. And what about the y prime? So the derivative, so m, which is the derivative of the function f at the point 1. So what do I get when I put 1 into the derivative? I get -3 times 1 squared plus 14 times 1 plus 5. Okay, I won't do the same mistakes as before. Let's calculate it carefully. 1 squared is 1. 1 times 3 is going to be -3. 14 times 1 is 14, and then 5. So let's see. -3 plus 5 is going to be 2, and 14 plus 2 is going to be 16. So the total there is 16, and great. So we know that m is 16, we know that y1 is 10, and we know that x1 is equal to 1. Okay, great. Now that we have all this ready to go, we are finally ready to find the equation of the line. So back to the equation of the line, y minus y1 equal to m times x minus x1 becomes, with the new numbers that we just found, it becomes y minus the 10 equals to 16 times x minus the 1. So this is x1, and this is the y1, and this is the m. Technically, this is the n, but I'll always like to write the y by itself so that when you have to graph it, it's easy to graph it. So I'll do that next. So I'll start by writing down y minus 10 equal to 16x minus 16. And I'd like to move the -10 to the opposite side. So I'll need to add 10 to both sides. So this gives me y equal to 16x, and then -16 plus 10, which is just -6. Let's just do that. So this is the equation of the tangent line that we're looking for. Okay, so great. So now the question is to find where the function f of x, which is the same function as above, where does it have a horizontal tangent line? So this function f of x, it looks like some kind of a cubic. There's probably places on the graph where the line tangent to the curve is going to be horizontal. We want to know what is the x value where that's happening. That's kind of what's going on here. So the first thing I need to do is recall the derivative. So my function is -x cubed plus 7x squared plus 5x minus 1. And we found, so I'm going to write recall, we found that f prime of x, the derivative, was -3x squared plus 14x plus 5. So this was the derivative of the function f of x. And we want to know where it has a horizontal tangent line. By the way, horizontal lines have slopes equal to 0. So in other terms, what they want me to do is this. They want me to solve the problem where I have f prime of x equal to 0. So I need to figure out what makes the -3x squared plus 14x plus 5 equal to 0. Once I find the numbers that make it equal to 0, I'll be able to distinguish or find that they are the places where the graph has a horizontal tangent line. Now, how do I solve something like this? You can either use factoring techniques or you can use the quadratic formula. It's up to you. But I think for me, I'll start by doing some factoring. I also don't like the fact that there's a minus in front of my problem. So I'm going to divide this guy by -1 and do it on all the terms. And this is perfectly legal as long as I do it to both sides of the equation, left and right. And this makes it so that it's 3x squared minus 14x minus 5 instead, all equal to 0. I prefer not to have a minus in my leading term so that when I use the big X method or whatever, it's a little bit faster, it's a little bit easier. So let's see. I will try to factor it by looking for two numbers that multiply to -15. but when I add them, I get negative 14. So can you think of two numbers that when you multiply, you get negative 15, but when you add, you get negative 14? I'm thinking 15 and 1 will get the job done as long as you go with negative 15 and positive 1. Seems like those are the numbers I want. And because I have a leading term with a 3 in there, that means I gotta write down some extra details in the middle. So I'll just start by writing the 3x squared minus 15x plus 1x minus 5. We've covered how to factor like this before. Basically, your middle term gets broken down into two new terms. These are the same numbers that you found in your product sum method. I like to call this the big X method. So whatever numbers you find in it, just put them in the middle. And now you have to do factoring by grouping. So what does this group of two factors have in common? It seems that they both have a 3 and an x. That leaves us with x minus 5. And what about these two guys over here? What do they have in common? Well, technically nothing, but I can always factor a 1. So that leaves me with x minus 5 also. So remember, 1 times x is just x, and 1 times negative 5 is negative 5. So I really haven't changed the problem by doing this. I just put an extra 1 there so I can see clearly what's going on. So now I do factor by grouping again. What does this group have that this group also has? It's the x minus 5, and when I factor it, I get x minus 5 times 3x plus 1 equal to 0. So according to my zero product property, either the x minus 5 has to be 0 or the 3x plus 1 has to be 0, which means either x is 5 or x is negative 1/3. So at these locations, I should be able to see a graph that looks sort of horizontal for a split second. So let's verify this by putting everything into the calculator. So what we want to do is go to our y menu where we graph everything and type in negative x cubed. So to put x cubed, I'll use the caret and then 3. So this is the sign above the division sign. So I type negative x and then I carry the power to 3. And next I have the 7 and x squared. For the power 2, I have a special button right above the log button next to 7. So that's the square button. I don't have to do the caret thing, but you can. There's nothing wrong with that. Plus 5x minus 1. So this is the given function f of x. And I'm going to graph it on the standard zoom. So zoom number 6. And this is what the graph looks like. I don't see all the different portions of the graph, so let's go ahead and modify the screen a little bit so we can see the bottom, the top, and so on. So I'm going to go to my window, and I want to see more of the top of the graph because it seems like it goes high. So I'm going to modify the y maximum to be 20 and see what happens. Okay, it still looks very high. So I can go and try this again. I'm gonna try to overkill it with like 100 on the Y max. And there you go. Now we can see the whole graph. We discovered that the solutions are negative 1/3 and 5. At those locations, apparently, there's a tangent line that is horizontal. So let's trace those locations real quick. So first of all, let's click on 5. And as you can see, 5 is kind of the tip of that little parabola shape thing. And apparently there we have a horizontal tangent line. And it seems to be kind of right. That's the place where the curve is turning around for a moment. It's going to be a little bit horizontal. The other location we found was negative 1/3. So if I trace negative 1/3, you'll see that puts me kind of on the bottom right there, which again, the function seems to be turning there. That's a low or a high point. In this case, it's a low point. So at the low point, it seems like the graph should be turning and should become horizontal for a split second. So our prediction was kind of correct. The only difference is our graph was upside down. So instead of having the graph the way I drew it, it's sort of like it starts really high, then it goes low, and then it goes high again. So at this moment in time when it's turning, the graph becomes horizontal for a split second, and that's the place where x was negative 1/3. The other place was 5. So at negative 1/3, we were horizontal for a moment. At 5, we were up here, and we were horizontal for a moment. Anyway, it's good to confirm with the calculator that the graph is doing what it's supposed to, but that's basically the whole point of this. The last example in this section deals with a little story. So we have a toy manufacturer that has a cost function for a particular toy given by c of x equals to 100 divided by x squared plus 8. Now, c in this case is the cost and x is the number of toys produced. And the cost is measured in dollars. So great, that's all written. I'm being told this little story. So the first thing I need to pay attention to is that they want me to find c prime of 2 and c prime of 5. And also they want me to explain what these things mean. So remember, this is the derivative and this is the derivative. And I'm given a cost function. So in a way, they're saying we want you to find the derivative and we want you to explain what c2 prime is and c prime of 5 is. Okay, there's a little graph section here in case you want to graph this function, but let's go on a calculator and graph it and see what it looks like. So again, as usual, I'm going to go to my Y menu and I'm going to type in the given cost function. So the cost is 100 divided by x squared plus 8. I need to be paying close attention to the denominator here. It has multiple terms, so I need to put some parentheses around everything, but that's basically what the cost function looks like. And I'm going to reset my window by clicking on zoom and then choosing option number 6, the standard zoom, and that's the graph. Now obviously x represents the number of toys and x can't be negative, so we can modify the screen a little bit so we can see more of what's going on. Ultimately, I'd like to know what's happening in the first quadrant. So let's go to window and get rid of the negative toys. That can't be a thing. And on the paper, my graph goes up to 12, so I'll just put 12 for x max. On the y minimum side, we are going to put 0 for the y minimum. And for the y maximum, it seems on paper they want 14, so I'll just use 14 there as well. So we can see this beautiful curve on our screen now, and if you want to take a moment of time to copy it to the paper, that's great. If not, that's not a big deal. What I want to trace real quick is just the value 0. This is the cost of not making any toys, basically. So if you make 0 toys, the cost is still going to be 12.5. That's associated with the fixed costs, right? You have to rent maybe the utilities or the place where you're producing the toys or whatever. So the fixed costs are basically 12.5. And as you make more and more toys, you see the graph kind of goes down a little bit because you're getting more efficient. Maybe you're getting deals from the raw materials or whatever. So that's why the graph kind of looks the way it does. Anyway, that's the graph, but we want to know c prime of 2 and c prime of 5. Now for those, we'll need the derivative, but we have a cost function, c of x, which is 100 over x squared plus 8. Now for this cost function, it's not possible to use the basic differentiation rules because my denominator has multiple terms, so therefore I can't use the basic rules. I need to use the quotient rule to get the derivative. So for now, we will start by setting it up like we did before. We'll write down the f function, and f is the numerator. And we'll write down the g prime and the g. The g is the denominator, which is x squared plus 8. And f prime is going to be the derivative of 100, which is 0 because 100 doesn't have any variables. The derivative of 100 is going to be 0. Great. And what about the g prime? The g prime is the derivative of x squared plus 8. Derivative of x squared is going to be 2x, and derivative of 8 is just simply 0. But derivative of 0, I'm not going to write it down because 2x plus 0 is just going to be 0. And this is a fraction problem, so we're going to need a quotient rule. So we'll multiply f prime with g, then g prime with f, and subtract along the way in the middle. So that's how that's going to work. Now later on, in later sections, we will be able to rewrite this problem in a different way that will allow us to use something called the general power rule or the chain rule. But today, we don't have that yet, so this is the only way to get the derivative, unless you want to use the limit definition, which I highly do not recommend for this problem. It will be very, very difficult to find the derivative of c using the limit definition.
So in any case, the c prime of x is going to be a fraction. And again, just like before, we're going to multiply some corners with each other and subtract the answers that we get. So we're going to multiply these corners. I'm highlighting them with color so you can see what I'm going to be doing in a moment. But first, we multiply the 0 with x squared plus 8. Then we subtract the product of 2x with 100. Okay, so the 0 because that's the derivative of f, the x squared plus 8 because that was the original denominator. So we take the derivative of the numerator, we leave the denominator alone, then we subtract. And what about the second term? The second term is going to be the 2x, the derivative of the denominator, times the original numerator. So like I said before, the numerator and denominator take turns basically, and we have to divide by the original denominator with the square on the outside. So let's get rid of all these colors, and when we do that, 0 times x squared plus 8 is going to be 0, and negative 2x times 100 is going to be negative 200x. But you know what? Let's not bother with the 0. Let's just put negative 200x divided by x squared plus 8 with everything squared. So this is my derivative function, and we are basically done finding the derivative, but we're not done with the problem, because they didn't say we want the derivative. They said we want c prime of 2 and c prime of 5. And also they want me to explain their meaning. So for c prime of 2, what is it going to be? How would I get c prime of 2? This is basically saying take the c prime function and replace all the x's with 2. So it's going to be a bunch of 2's entering, right? So wherever the x used to be, we're going to replace it with 2. And you can use your calculator to get the solution here, but in any case, I'm going to get something like negative 400 on the numerator, and 2 squared is going to be 4, 4 plus 8 is going to be 12, 12 squared on the denominator is the same thing as 144. So roughly speaking, this is negative 2.78. And we'll worry about the units in a second. I'll describe what the units have to be. For c prime of 5, pretty much the same idea. We're going to take negative 200 and we're going to multiply by 5, so replace the x with 5. Same thing again, 5 squared plus 8, and we will square the denominator. So again, I'm taking the original c prime of x and I'm replacing all the x's with 5 because that's what the question asked me to do. And this is negative 1,000, all divided by 5 squared is 25. 25 and 8 is going to be something like 33 squared. And roughly speaking, when you put this in your calculator, you're going to end up with negative 0.92. Now remember, the cost is in dollars, so the derivative is going to have dollars in the numerator, and this depends on how many toys you're making. So it's basically dollars per toy is the unit of this function. The regular cost would be just dollars, and here it's dollars per toy. So what's going on is from the graph, we saw that the graph kind of did this earlier. We saw that it went down, and we are basically saying that as you make more and more toys, the cost seems to be decreasing. And that's something that's kind of intuitive, right? The more toys you make, the more deals you can get on raw materials, and because you're making economies of scale, the cost per toy is going to decrease. And what is exactly c prime of 2 and c prime of 5? What do these numbers themselves mean? And by the way, these are the answers that we were looking for. So what does it mean to say that c prime of 2 is equal to negative 2.78 approximately? Basically, it tells us that if 2 toys are produced, the cost per toy is decreasing by $2.78 roughly per toy. And what about c prime of 5? Well, c prime of 5 basically tells us that if 5 toys are produced, the cost per toy is decreasing by about 92 cents per toy.